Now we're going to transition out of integrals into sequences and series. And when you first see this, it may seem like a completely new topic, no relation to the previous material. But really what we're doing is we're going to be doing the same thing conceptually in the world of discrete versus the world of continuous. So I'd just like to take a moment to kind of give you an idea of where we're headed with all this stuff. So first of all, we'll look at sequences. And a sequence would be something like 1, 1/4, 1/9, 1/16. And a sequence is sort of the discrete version of a function, right? I could put a formula for that. Sequences we usually refer to by their terms, but and we'll talk about this in more detail in a little bit, but really this is 1 over n squared. And we use n specifically to mean that you're only plugging in natural numbers. So when n is 1, you get 1. When n is 2, you get a 4th. When n is 3, you get a 9th. And this goes on forever. Well, this is like taking the function f of x, 1 over x squared. We're familiar with that. Really all it is those are a series of dots on that, right? This function, you're allowed to plug any x in you want, any real number, so long as it's defined. Here, you're only allowed to plug in the naturals. So they're very closely related. If we were to graph them, and this axis will represent x or n. This axis f of x or a sub n. The function is continuous, right? It's a continuum of points. Looks something like that. The sequence is only these particular points, right? Where n is 1, 2, 3, and so on. So it's a series of dots. If we think of it graphically, those would keep going. But they're very closely connected. Those dots are on that curve. So there is some sort of connection between the world of continuous functions and sequences. So we'll look at sequences first. And again, it's just a domain issue, right? We're switching our domain to not the real numbers, but the natural numbers. And then what did we do recently with functions is we did integrals, and specifically improper integrals. And those relate to what we call series. A series you can think of as just the sum of a sequence. So instead of just a list of numbers, it is summing them up. And it's an infinite sum, right? We're going to be adding up all the dots, if you like, on that curve. Well, it's very closely related to the improper integral. Actually, let me use the symbol we would use here. This is the sum, n from 1 to infinity of 1 over n squared, versus the integral from 1 to infinity of 1 over x squared. These two things are very closely related. It may not be obvious how right at first. Let me redraw this picture, but just focus on the part where the sequence exists. I'm going to draw it again over here. So here's our x or n axis, our f of x or a of n axis. And so I'm going to start at 1 at 1 there, and I'm going to distort this a little bit because those numbers get small pretty quick. So I'm going to have the scale be stretched quite a bit here. So we start out when x is 1, we start out here, and we rush down to the axis like that. That is f at 1 and also the sequence at 1. Now, let's see how those two might connect. Well, if I draw a rectangle, like that, the area under the curve is part of this integral, right? It's the very first part from 1 to 2. But think about the area of that rectangle. Its height is 1, and its base is 1. So it's got area 1, which is the first term in that sequence, in that sum, right, in this sequence, but here we're adding it up. Now, the next one at 2, the height there is a 4th, right? Again, I've distorted this scale just so we can see it. But the idea is the heights of these rectangles are being determined by that curve. It's got height 1/4, base 1. So the area of that rectangle is a 4th, which is the next term. And so on. 9th, 16th, 25th. So they're not equal to each other, right? These rectangles are not the area under the curve. Clearly, they all stick out some. But the idea is that there is a connection. There is some sort of connection between these two because the area under the curve has to do with the height of the curve. And the area of these rectangles has something to do with the height of the curve. It's only these heights are only getting determined, though, every 1 unit down the axis. So they're not the same, but they are related. And as we're going to see later on, whatever happens with this integral also happens with this sum. So if this integral is divergent, that sum is divergent. If this integral is convergent, this sum is convergent. And actually, we know already, right, this integral converges. It's one of our reciprocal power functions. So it's going to turn out that that series converges. Now, what it converges to is a whole other question. But we do know that this sum will converge to something because of this connection to the integral. Now, the reason that we're interested in series, at least in here, is to get us to what are called Taylor series. And so sort of the payoff at the end is after we look at sequences, we'll look at properties of sequences. And then sequences are the basis for series. We'll look at these series, and we'll look at different techniques to try and determine if a series converges or diverges. And then we'll move on to what are called Taylor series, which a Taylor series writes a function as an infinitely long polynomial. If you think of a polynomial as terms, a constant term, a first-degree term, a second-degree term, a third-degree term, a Taylor series takes that on forever. So the polynomial has infinitely many terms. For example, we'll see something like sine x actually turns out to be equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on forever in that pattern. Now, why do we care about this? Well, we have to remember, we often forget in the world of calculators that we don't know how to calculate values of sine. It's a transcendental function. What that means is I can't give you a formula for how to calculate sine. It cannot be done. Now, we can get certain values of sine by geometry, right? We know sine at 0, pi over 6, pi over 4, pi over 3, pi over 2, and other angles. But if you just want to know what is sine equal at some arbitrary value, I can't give you a finite formula that'll give you that value. Finite being the key part. That's transcendentals cannot be written in a finite formula. But if we remove the finite part, we can do it with a Taylor series. It's an infinite formula. And the idea is, even though it's infinite, as you bring in more and more terms, it gets better and better at approximating that function. So this is going to give us a way of computing approximations of this, and we can make the approximations better and better by using more and more terms of that infinitely long polynomial. And it turns out we can do this with all the transcendentals. Sine is transcendental, all the trig functions are transcendental, all the inverse trig functions, log functions, e to the x. So all of those powerful transcendental functions we have really don't have a way for us to compute them until we have these Taylor series. And so the series that we'll look at the beginning will just be a list of numbers. But then we're going to introduce a variable into that series, and that's when we'll start to write functions as series. And that's the real power of series, is the ability to take something transcendental that up until now we didn't know how to compute and give us a way of computing it to whatever accuracy we like. So that's where we'll be for a while. It's still very similar to what we've been doing, right? We used to look at functions, now we look at functions still, but only evaluate at natural numbers. We looked at areas under a curve forever, which is really an infinite sum, right? It's the summing up of that area forever. Now we're looking at infinite sums, but it's not continuous. It's this discrete situation. So that's what we'll be looking at for the foreseeable future anyway.